So that's the end of the sort of general overview of the course. Now we go through the details of the course, and we chop that rather arbitrarily into three separate lessons to keep the lessons of reasonable size. Each of them is about 5 slides. I should point out that the unit counts are sometimes a little less clear than they could be, because in this presentation here, I don't distinguish the Java unit from the Python unit, whereas if you actually look at the course, they're actually separated. So when I say 1 unit, it might appear as 2 units if there's a separate Python and Java version. All right, we start with this motivation unit I described, which is introduction, like we must have an introduction. Data deluge, jobs, industry trends, computing model, research model, how you do research, the so-called fourth paradigm, which is data-driven science, following on observation theory and simulation. What data science is and what is the process of doing data science. Some examples which are actually come from this class. The physics informatics, looking for the Higgs particle with the LHC, Large Hadron Collider, recommender systems, web search, cloud applications, parallel computing and MapReduce, data science education. That is something which is actually not described in the course, because the course is part of data science education. And then we have some simple conclusions. So that's that unit there. Now we come to 3 units on which are the introduction to the course. And not surprisingly, the introduction to the course is some similarities with the motivation for the course. So you'll see some similar topics. We start off with a discussion of what is informatics and its rallying cry, jobs, the data deluge and general structure, process of data science, examples of the data deluge for internet, business, and science and research, science, engineering, and research. And then we look at the implications of scientific method, because as we mentioned actually a little earlier, there is the so-called fourth paradigm, because we have theory, observation, simulation. Those are the first 3 paradigms of research. Now data-driven research is the fourth paradigm. Then we have the long tail of science. You can get big data by having a huge accelerator pouring out data. You can get little data by having lots and lots of users, each with their own sensor or set of sensors. And the long tail of science is those lots of individual users, each with a modest or smallish amounts of data, but the sum over I of a small number over a big enough value number of I can be a big number. And then we go to this very important Internet of Things. The number of things on the internet is increasing 31% compound-wise year to year. We're going to reach 75 billion by 2020. Then we discuss clouds, features of the data deluge, the data science process again, and data analytics. Now we have a unit which is one of these side MOOCs discussing Python. It has an introduction that discusses one of the available Python resources, Canopy, which includes IPython. And then we have discussions of NumPy, discussion of Matplotlib, and discussion of SciPy. So this one of the big advantages of Python. It has built-in, it's an interpreted language, effectively, which has a lot of built-in capabilities to do scientific computing. And the plotting package, Matplotlib, is, I don't know if it's the best plotting package, but it's not too bad. So that's a side MOOC. Then we have another side MOOC on using clouds, big data analysis. This is currently focused on FutureGrid, how you create an account, how you upload your OpenID to get that account, how you create and upload an SSH key to get secure access to FutureGrid, how you join the project associated with the class, how you log into FutureGrid, how you access IPython virtual machines, how you log into virtual machines to do more sophisticated things, and how you run Java on FutureGrid. So that's the second side MOOC. After that side move, we return to the core intellectual part of the course, and we do the value of x equals physics, and in particular how we discover the Higgs particle and all the issues involved in counting lots of events and the statistics involved with them. So that covers looking for the Higgs particle and an introduction to counting errors. Um, and then we look at the experiments, and then we have a little picture gallery of accelerators. We discuss event counting in detail, and we give some examples with Python and Java, especially Python is particularly good for these types of examples because of its nice graphics. And then that's for the signal and background. We look at those issues. Then we look at some sort of fundamental analytics issues, random variables, and the use of random variables in physics. The statistics of events with so-called normal or Gaussian distributions. Then we look at random numbers and how you generate them and what their seeds are, and we do that with Python and Java. Then we look at a particularly important distribution, the binomial and Poisson distribution. We use the so-called accept-reject method, which is one of the more important ways of generating general distributions. The distribution tells you what the relative probability of particular events is. We use the Monte Carlo method. Physics is notable for generating at least as much data from Monte Carlo as it does from the accelerator. You need Monte Carlo, which are simulated events, to try to understand these complex events, which are giant pieces of apparatus, and what, when you see something in them, does it really mean? So after the binomial leads on to the Poisson distribution, and then the so-called central limit theorem. So that's those 4 units. They cover not only physics and this application, but also fundamental simple statistics.